Today we will talk about the passive second-order RC low-pass filter, which is a natural extension of the filter we studied in the last episode. Before starting with a new subject, I will spend a couple of minutes to clarify an issue from that previous video. The most part of this video is dedicated to lab experiments to show you the effects of the filter, to take some significant measurements on it, and to compare it to the first-order filter. And of course, I will provide you with answers on why the two filters behave differently from each other. Before moving on, please take a moment to also subscribe to the channel and don't forget to click on the notification bell. This will send you automatic notifications every time a new video comes out. But make sure you enable the notifications for the YouTube app on your phone, or you will not realize you have received them. Your phone app has become the only way to receive notifications since YouTube has stopped sending them via email. And if by any chance you are planning to buy some lab instruments, like the ones I am using, I posted a couple of affiliated links in the video description below to help you out in the choice. They are the same instruments you'll see throughout the video. And now, let's begin. Before getting into the merit of the video, I would like to spend a couple of minutes to describe what happened when I measured the attenuation slope of the first-order RC filters. The actual slope of a filter is not constant for any frequency, but it is actually a function of it. If you look at the bot diagram, you can see that before we reach the cutoff frequency of the filter, the slope is basically zero. When we approach the cutoff filter, the slope starts changing gradually, but at the exact cutoff frequency, it does not yet have its final value. In fact, it continues to increase negatively until only far away from the cutoff frequency becomes a constant. It is this last value that is the one that we accept as the attenuation of the filter, and you can see from the diagram that for first-order filters we need to reach a frequency of about 10 times the cutoff frequency before we reach the point where the attenuation becomes constant. For the filter in the previous episode, the cutoff frequency was around 16 kHz, and therefore the attenuation does not change anymore when we go past the 160 kHz. This is the base frequency at which we should measure the attenuation of the filter, not a smaller frequency. But unfortunately I dismissed entirely this problem in the previous episode, and so I ended up taking the measurement in an area of the diagram where the slope was changing and at that point was only 10 dB per decade. In reality, I should have taken the measurement at a higher frequency to avoid the error caused by changing the shape of the diagram. The fact is, the correct measurement should have been in the 20 dB per decade range, as the theory suggests. Because of that, I went back to the lab and repeated the measurements in the right way, and I am now showing how I did it. After that, we will start talking about today's topic. Okay, let's redo the measurements for the first-order low-pass RC filter. This is the same circuit as in the last video. It is already connected to the noise generator through this cable, and goes up here where I already set white noise and it's on, and the output is connected instead to the oscilloscope, which is now representing the noise in its time domain screen. So now let's move to the frequency domain. This is the spectrum of the filter. Right now it is set with 1.25 MHz range. Now let's talk about this a little bit. Let me reduce the frequency here. So we are now centered at 6.25 kHz. We know that this filter has a cutoff frequency of about 16 kHz. Here we are before the 16 kHz, so before the cutoff frequency, it is basically almost flat. I'm gonna change the setup here so that we can see what happened at higher frequency. Here we are at 12.5 kHz. You see it's still flat, but it started bending a little bit. If we move it a little bit more, now this is centered to 25 kHz. You can see that now it is already in its knee of the curve, but it's still not much change from this side here, which is 0, to this side here, which is 50 kHz. And this is because there is that knee where the slope of the attenuation keeps changing. So now let's increase the range of the oscilloscope so we can see what happens at higher frequency. See here, the slope keeps changing. We are centered at 62.5 kHz. Let's go a little higher You see, now we can see the slope changing better, but we are still in the part that where it does not decrease constantly. So let me move a little bit further, and here, let's stop over here. You see now there is this interval here where it basically changed the way we want it. We are far away from the cutoff frequency now, so we now can make a reasonable measurements about the attenuation slope. Let's turn on the cursors. Okay, first of all, what we want to do is to identify the interval where we want to make our measurements. Since we are centered at 625 kHz, probably the best thing is to start from here, which is 125 kHz, up to the end, which is 1.25 MHz. So here the frequency is exactly 10 times what is here. So I'm gonna use the magnitude cursors to show you what happened now. Let me zoom in so you can see better what happens. So let's begin with the start cursor, and I'm gonna adjust it here. Basically on the left of this line now we have still the both diagram on the upper side. On this side instead there is the lower part. So this is the crossing point. Now let's set the end cursor, and we have to do it here on the border, and the crossing point seems to be about here. So this is the drop in signal, so the attenuation of the system for a decade of frequencies, and we can read here the value. It's at 20.80 dBs, of course with the approximation that I made in doing this graph. So we can see that we have actually 20 dBs per decade if we do the measurement correctly. The schematic for a second-order RC low-pass filter can be easily made starting from two first-order filters and connecting the output of the first filter to the input of the second, basically putting them in cascade. The result is this schematic. Let's see in lab how this filter behaves. For the experiment, and to have something to use as a reference, I have used the same exact components from the previous video. A 10 kΩ resistor and a 1 nanofarad capacitor. We will check out first how the output voltage changes with the frequency, both in amplitude and in phase, and then we will measure the cutoff frequency, and finally the infamous attenuation rate. Okay, here are the two first-order filters connected together to form a second-order low-pass filter. And here is the signal coming out from the function generator, which is gonna be a sine wave again. And I'm gonna connect the oscilloscope on this other side, on the output of the second filter. And as I just said, the output of the first filter goes directly into the input of the second filter. Here is the rest of the settings, the oscilloscope that we are gonna use, and the function generator and the noise generator. Right now I have connected again the function generator to the blue channel of the oscilloscope, and on the yellow channel there is a signal coming from the filter. So let's start with a low frequency, and let's see the behavior of this thing. Okay, here we are very low, and let me move this so you can see what's going on. You see there are two signals that are practically identical. I just superimpose them so you will easily see how the amplitude and the phase shift change simultaneously. Now I'm gonna increase, like I did in the previous video, the frequency a little bit at a time. And I'm gonna keep adjusting also the oscilloscope to change the scale so you can see better what happens. You see there is already a slight difference over here, and we are at 400 Hz right now. It's gone. Now we are at 1 kHz. And note how the phase shift starts showing up. And at the same time you can see that there is a slight change in amplitude. But right now the change is minimal, so really we can consider this as negligible. Let's increase the frequency a little bit, and now let's move from 1 kHz to 2 kHz. Let me enlarge this again, so you can see now we are at 2 kHz, the phase shift has increased a little bit, as well as the amplitude. Let's move to 3 kHz, 4, 5, look, at 5 kHz we are already in this condition. There is a shift which is still relatively low. Let's increase further. Look at the amplitude of the signal now, which is almost cut in half, and the phase shift, look closely at that. Can you see it? It's almost 180 degrees. It's not anymore 90 like in the previous filter. Let's increase a little bit more. Now we go to 10 kHz. See, the phase shift has increased even further. And now we are at 14 kHz. And look at the phase shift. Now it's basically 180 degrees exactly. And the amplitude now is 2 for the output, and the input was about 2, 4, 5 squares, so now it has become already 2/5 of the original size. And at this point, if we keep increasing, things will go change again. But look, now the phase shift doesn't change anymore, has remained to 180 degrees, but the amplitude keeps changing. This means that we have already exceeded the cutoff frequency, and so now we are purely in the part of the filter where the slope starts decreasing steadily and faster. Look what happened at 35 kHz. Let me increase the scale of the yellow signal so you can better have an estimate of how the phase shift change. So this is 200 millivolt for the output, while the input is about 1 volt per division. So the input is basically 5 volts, while the output is 2, 4, about 650 millivolts. So now if we increase even further, so this is 50 kHz, 60, 70, 80, 90. See, the phase shift does not change anymore at this point. It's basically constant 180 degrees, but the amplitude keeps changing steadily. Now let's go back with the frequency. Let's go back down to about 1000 Hz. And let's put this back to its original value, so we are back at the beginning, like we saw before. So this is for how the voltage, amplitude and phase changes from the input to the output. Let's measure now the cutoff frequency of this second order filter. Here is the setup. This is the filter with this first stage and the second stage, and the input of this filter will be connected to the noise generator over here, and the output of the filter instead is connected directly to the oscilloscope. So if we now turn on the function generator, the noise generator in particular, on white noise, we can see on the oscilloscope that we have its representation in the time domain. Now let's move in the frequency domain and let's see what happens. Here is our representation. You can see that the signal goes down and is attenuated more and more the more the function increases, as we expected, of course. Now let's give it a try to measure the cutoff frequency. We are gonna need to use cursors, and I'm gonna set up them for magnitude. We need to differentiate the cursors so that they are distant from each other 3 dBs, so we can measure the drop in 3 dBs in the amplitude of the signal in the frequency domain, and that will tell us how much is the cutoff frequency. So let's start with the first cursor, the start one right here. Let's adjust it right here, so it'll be easier to make the measurements right on the line represented by the oscilloscope. And then the second one, which is gonna be 3 dB differences, so we can read it from here. And now let's lock the cursors so they won't move anymore. So they will move together now, you see. So now let's get to the point where the signal is maximum. And it's about here, right? And now with the second one, let's see where it goes down, when the signal goes below this line and doesn't come back anymore. It's happening about here, right, on the second division. So basically the cutoff frequency is gonna be right here. This is 0, and this one is, since we have a 2.5 kHz per division, this is gonna be about 5 kHz. So our cutoff frequency for this filter is now about 5 kHz. Okay, let's take now the measurement for the attenuation rate. This is the circuit. We have the noise generator connected over here and the oscilloscope over there, and here is the noise generator set on white noise, and the oscilloscope is showing us already the cursors posted already at the beginning and at the end of the part of the body diagram that we want to measure. And if we take a look at what is the magnitude that they are representing, it's about 38.4 dBs, which is what the oscilloscope along with the noise generator is able to measure. It would seem that just by cascading a couple of first-order filters to make a second-order one would keep the same cutoff frequency while doubling the attenuation and the phase shift. But we have seen in lab that this assumed behavior is only partially true. Let's take a look at the diagrams to understand why. These on the left are the diagrams for the first-order filter, and these on the right are those for the second-order filter. Now, it is true that the attenuation doubles, going from 20 to 40 dBs per decade. If you look at the two body diagrams, you can see that the shape of the curve is exactly the same, but the scale on the y-axis, the one that represents the attenuation of the signal, are different. The diagram for the first-order filter has values going from 0 down to minus 60 dBs, while the diagram for the second-order filter has values from the same frequency range from 0 dB down to 120 dBs. And that confirms that the attenuation of the two first-order filters in series that makes the second-order filter adds up and therefore doubles. And it is also true that the phase shift doubles, going from a maximum of 90 degrees to a whopping 180, according to these pictures. And that's exactly what we have seen in the lab experiment. But in the same lab experiment we measured a cutoff frequency definitely lower than the one on the first-order filter. Why this change, and why only this one? The truth is that there is no change whatsoever in the concept. So why the change in the measure of the cutoff frequency then? Well, first, remember that we have defined the cutoff frequency as that frequency when the attenuation becomes exactly minus 3 dBs. We have seen that the attenuation has changed, going from minus 20 dBs to minus 40 dBs per decade. It is basically the sum of the two individual first-order filters in any point of the body diagram. But then, now at the point of the cutoff frequency for the first-order filter, which was 16 kHz, the attenuation for the second-order filter is no more minus 3 dB, it is now minus 6 dB, and because of that, the same point on the diagram does not satisfy anymore the 3 dB rule. So now we have to find another point where the attenuation is minus 3 dB, and of course that point must be at a frequency value smaller than the one for the first-order filter. And if we look carefully at the diagram on the right, we can see how this frequency is about 5 kHz now. A drastic change from the first-order filter case. Now, using some algebra, we could also calculate the exact value of the cutoff frequency. However, I am not going to show you the math here, since it is a long and boring calculation. And you don't want to be annoyed by that and stop watching the video, right? So, I'm giving you directly the final formula to calculate the frequency given the value of the resistors and the capacitors. This formula assumes that both resistors have the same value, and the same for the capacitors. And the formula is Fc equals 0.048 over the product of R and C. We can rearrange this formula to calculate the RC product based on the frequency value, and this becomes useful when designing a filter. And this formula can be rearranged to determine the resistor based on known frequency and capacitance, or to determine the capacitor based on known frequency and resistance. Let's take a look now at the response to a square wave. I have connected the output of the second-order filter to the yellow channel of the oscilloscope, and I have also connected the blue channel of the oscilloscope to the first section of the filter, which is basically the first-order low-pass filter. This way we can compare the output of the first order and the second order and see what the difference is because of what changed. Again, I am using a square wave to do that, as you can see, and is set right now at 1 kHz and 5 volts output. And this is what the oscilloscopes tell us. So the blue one is the response of the first order filter, and the yellow one is the response to the second order filter. The second order filter has an attenuation double the amount of the one of the first order, and so it deletes more harmonics of the signal. Therefore, it will remove from the square wave more harmonics than the one of the first order, and so the square wave becomes smoother with the second order filter, the yellow one, while it's still more rapid for the first order filter. This tells us that basically the more we increase the order of the filter, we go to the third, the fourth order, just by adding more stages to the filter, the response to the square wave will become smoother and smoother until it will become comparable to the one of a sine wave. Let's take a look at the whole thing now. You see, so it becomes smoother both when going up and when going down. If I increase the frequency, you will see that things will change more drastically. Now you can see more clearly a difference between the second order filter in yellow and the first order filter in blue. Technically, when the frequency is enough high, we should have an approximation similar to the one of a sine wave. You see how the filter of the second order has smoothed out, while the first order is still more spiky. So if we increase drastically the frequency, we can see a big difference here. Look at that. I'm increasing the frequency more and more. You see, the second order filter is almost now a sine wave. We are at 34 kHz, so way above the cutoff frequency, while the first order filter is still spiky with clear angles over here, while the second order filter is totally smoothed out already. And here's the response to an impulse. Again, this in yellow is the second order filter, while the one in blue is the first order filter. You can see how the second order filter is again a little smoother than the one on the first order. Here the peak is much more pronounced. Let me enlarge it so you can see it better. See? While in the second order filter there is a much smoother descending of the signal on the output of the filter. And that is because, again, this filter is cancelling more second order harmonics than the filter of the first order. Let's try to isolate one. You can see how this differs. A very brisk raise and then a relatively slow going down, while here the going up is less brisk and even less the descending shape. Let's compare them on top of each other. So you can see clearly that the second order filter takes a longer time to extinguish the response to the impulse. And that's all for the passive second order RC filters. Like we did for the first order filter, we have seen how the filter behaves at the change of the frequency of the input signal, and we have both measured and calculated the cutoff frequency of such filter, and we have seen how to design a filter that provides the exact cutoff frequency that we need. We have also seen how to take some basic measurements with the help of an oscilloscope, the cutoff frequency itself and the attenuation slope, as well as seeing the response to a step signal or square wave and the response of the filter to an impulse. Next time we will use a new component to make filters, the inductor, and we will see how to obtain a first order low pass filter with that. Thank you for watching this video, and please give it a thumb up, which will help to improve its visibility so others can enjoy it too. And don't forget to subscribe if you haven't done so already, so you can be automatically notified on your phone app of new videos. Consider also making a small monetary contribution that will help in the making of future videos for your enjoyment. Details are in the description below. And finally, consider using the affiliated links on the video description to reach Amazon website if buying something for your lab experiments or for anything else. This will also help the channel and at no cost to you. See you in the next video, and as usual, happy experiments!